Hi, greetings everyone. Thank you for joining us at Exchanging Ideas 39. I'm Kanishravan Govindasamy, the founder of Global 5G Evolution. A warm welcome to everyone, to all the speakers from around the globe. Thank you for joining us. Please take a couple of seconds to click the subscribe button on our YouTube channel. Today, I will be presenting the spectrum for 6G explained. As you can see in the slide, while today's most advanced 5G networks deliver the highest performance, technically feasible, developments in adjacent fields such as artificial intelligence, machine learning, semiconductor, and material science will allow future telecommunication networks to achieve even loftier goals. In 6G, we will experience the fusion of physical and digital worlds, which will transform the way we live and work. As you can see, I'm having an analyzing of Nokia slide here. What will 6G networks be capable of that cannot be achieved with today's 5G networks? 6G will not only enhance the fundamental features of 5G, but it will also come with additional enhancements in reliability, positioning, sensing accuracy, and foremost, energy efficiency. Multi-sensory and immersive communications will enable the true realization of XR. Metaverse and digital twins will be further advanced by 6G, while cobots will drive the needs for high accuracy sensing positioning as well. And reliability in complex industrial environments also is very key. And 6G must address sustainability and tackle digital inequality. Its success will be measured not just by the telecom industry's own contributions, but also by how it will enable other industries and governments to reach their sustainability targets. When will 6G arrive? We expect 6G towards the end of this decade and on a firmer footing early in the next decade. Through the WRC ITUR, it is expected to decide on the frequency bands and the conditions for 6G. 3GPP will need to conclude on the standardization requirements with the first 6G specifications expected to be available in 3GPP release 21 in second half of 2028. Decisions on candidate spectrum bands to be studied for 6G are likely to be taken out at WRC 23. Which will ensure that the usage conditions will be studied and become available by 2030. Now, do we need different spectrum for 6G? As we approach WRC 23, the questions that arise when discussing 6G candidate bands are, why more spectrum? Why now? How much? And from which frequency bands? This will be the favorite question. The global cellular traffic is growing yearly, and it will continue to grow throughout the decade. Studies estimate the cellular traffic volume will triple between 2022 and 2027. Therefore, additional spectrum will be required to support such growth in an economically and environmentally sustainable way. As you can see from the table, it is very clear that the Oceania or the Eastern Asia, Southern Asia will be much more demanding in terms of the requirements from the 5G towards to the 6G. Now, Nokia spectrum vision in the 6G era. One key learning from the introduction of 5G is that reusing the existing network site infrastructure with new spectrum is vital for network planning and cost efficiency. Nokia considers that to balance capacity and coverage, new mid-band spectrum from within the 7 to 15 gigahertz range is needed, as you can see in the green range here in 5G Advanced and 6G. Specifically from 7.125 to 8.5, 10.7 to 13.25, and 14 to 15.35. Focus on the ranges in the next ITUR study cycle would enable spectrum availability in the time for the introduction of the 6G before the 2030. Additionally, the 6G research is ongoing on sub-terahertz spectrum that can be useful for applications like high accuracy, sensing, and positioning. as the propagation characteristics of sub-terahertz frequencies do not allow for efficient delivery of capacity and coverage in wider area networks. Such spectrum can only complement the mid-band spectrums, not by replacing them. So initial 6G spectrum need calculations for extended reality, XR, and the holographic communications that has been developed by GSA recently with Nokia support as an active contributor. To address the needs of some of the 6G data-hungry use cases, the minimum wide area spectrum required is estimated to be roughly about 1 gigahertz, right? I repeat again, this spectrum required estimated to be roughly 1 gigahertz per network. And considering if 3 to 4 operators per country, and assuming that in the long term, the existing mid-band spectrum available for IMT will solely be reused to address the wide area use cases. And that is approximately between 500 to 750 megahertz of additional new wide area spectrum per network that will be needed between the 7 to 15 gig subband, right? So in conclusion, in addition to the currently designated spectrum, 6G will require new spectrum to meet the data demands by 2030. New spectrum will act as the enabler for the industry to meet its targets in the areas of efficiency, performance, and sustainability, while still maintaining a viable economic environment to attract investments. From a regulatory perspective, IMT identification of new spectrum in the extended mid-band 7 to 15 gigahertz will be vital for the industry. It can enable global and regional harmonization, provide a regulatory certainty for technological investments in the ecosystem, and also it enables the economies of scale needed for faster development and broader adoption. I think that's all from my side. Thank you so much. And I would like to introduce Monica Paolini from Seattle, USA, to present the energy efficiency as we move 5G to 6G. Over to you, Monica. I can't hear you. Would you mind to unmute?
Sorry, I was muted. Ganesh, thanks a lot for the introduction. And let me see whether I can get my screen to show. So Ganesh, you gave us a great introduction into why we need more spectrum. Now, I'm going to talk about energy efficiency. And this is like, it's a top of mind type of issue right now, a topic for all operators and everybody in the industry. I have a few sort of general facts here. And so first of all, and this might be, my presentation is going to be a little bit different from what you might hear about energy efficiency and sustainability. So first of all, we should actually be pretty proud in the wireless industry. We haven't done all that bad because if you think of the traffic increases being really high, we still managed to keep our consumption to grow at a much lower pace. And so mobile networks account for 0.7% of global consumption. And if you think how important mobile phones are for us, that's pretty good. This is only the networks, however, not the devices. And the consumption has grown 64% from 2011 to 2021. And in the same amount of time, traffic grew to 87%. So our efficiency, energy efficiency has grown a lot. So we're doing well. Renewable energy is used more often. So it's all pretty good. However, we cannot just stop here and accept and do, well, we're doing well, we don't need to do anymore. We need to do more, we can do more, and we can enable other sectors to do better. So we do have a big responsibility to do better because we're still very inefficient in the way we use energy. And this is going to get only worse in this, from a demand point of view, because traffic is growing. There is an increased growth in traffic, you know, we have been seeing for the last couple of decades. But also there is more use cases for IoT and enterprise networks, and then there's going to be the metaverse. Like God knows what, how much more traffic that will generate. And I mean metaverse, other type of use cases. However, it's also, we have to think about wireless as enabling other sectors to cut their emissions and reduce energy consumption, because we enable services that make it possible. So on one hand, we're going to see power consumption in absolute terms increase, but that's because also there is a lot of growth. Now, I don't want to talk about that. That should be pretty straightforward. I want to focus more on how does 6G fit in the path to higher energy efficiency. Now, when we talk about 6G, it's always a little bit difficult, because what is 6G, which is specific to 6G, and what is in general the evolution. So a lot of those of these things that are going to enable higher energy efficiency are not necessarily specific to 6G, but 6G is a way to think about it. It's a way to focus on them, and that's a way to funnel all the technological innovation. So there is going to be, the first one is there is a component evolution. Right, so there's going to be better, more efficient chipsets, better cooling systems, equipment that requires less cooling. So there is all sorts of ways in which we can lower the power consumption at the element level. However, I'm going to, at the end, mention a report I just wrote on this. My view is that this is clearly beneficial, but there's just so much you can do in order to decrease the power consumption at the element level. There is much more that we can do at the end-to-end level, and especially because that's where there is, I think, more of the inefficiency, or where there is more of a scope for change. And so as we go from 4G to 5G and eventually to 5G, we should expect the power consumption in the RAN as a percent of the whole end-to-end network decrease as the RAN becomes more efficient. However, this is also going to, we're going to see potentially, or there is a potential for power, increased power efficiency. Here, what I mean by potential is that we have operators the opportunity to deploy and operate the network in a way that's more efficient, but the energy efficiency depends on the usage level, depends on how you run the network. So there is a lot of things. So I'd rather talk about the opportunity for energy efficiency rather than in energy efficiency increases as a given. So disaggregation and open RAN might lead to an increased competition and increased amount of choice for operators, and will give them the opportunity to be more efficient, because they can deploy a network that really meets their energy and performance needs more closely. Cloud native architectures enables pooling gains that might lead to increased power consumption. It's not necessarily so, but that's clearly a possibility. Same with distributed RAN topologies. So both a centralized or the distributed RAN might be more efficient. The question is, what is more efficient in your network at your location? And so it's the flexibility that really matters here, rather than the centralized versus distributed RAN. They both can be more energy efficient, depends on how you optimize it. A very important thing is the better management of sleep modes. So basically, at what point you can either lower the power consumption of a specific element, or deactivate. For instance, you can now deactivate single cores in a server, so you can have all sorts of big server, but if you don't need it all, you just can switch off part of it. However, this is not really what I wanted to talk about. So all of these features here are quite important, and they're going to be play the major role. Okay, so this is like the path to improve the energy efficiency. However, what I think it's different in a sense that it's a qualitative difference. It's something that we do not have really today. And so those are the kind of things that when I think about it, I think more about 6G, because this is truly new. It's not an incremental change, it's a qualitative change, introducing something that we don't currently use much. The first one is sensing. And as kind of says, sensing is coming. And it has all sorts of reasons, all sorts of advantages and reasons why we want to have sensing. But there is one aspect of sensing, which is increased energy efficiency. And this is because with sensing, with the level of sensing that has a great accuracy in terms of location, in terms of you can do what you can sense, you have a better way to control the environment, to know what's going on, to even act on it. And so this is quite important when you think about utilities, transportation, manufacturing, and healthcare. There's a lot of applications, a lot of use cases where we, as the wireless industry, can lead to improve efficiency in other sectors. So there is the estimate of I think 15% reduction that we can generate. It's difficult to know how much it is, because it's difficult to know how much is would wireless connectivity be responsible. But I think that you'd agree that there is going to be a clear advantage, and sensing is going to be a really important part of it. And you can also use it in wireless to monitor and optimize the way mobile wireless networks work. So it's for other sectors, but also for us. And also RIS, which is the next thing, can also be used for improving sensing. So there is improvements in the as we go through 6G, that will also enhance energy efficiency, well, sensing, and therefore energy efficiency. Now, RIS, which is reconfigurable intelligent surfaces, is a new thing. And I'm going to say what it is, even though you probably know what it is. But I still find that there is very little awareness, and nobody is really even willing to really talk much about it. However, ETSI has published a few documents of it, and there is a lot of work that's being done, a lot of it in China, but not just there. Basically what RIS does, it enables passive transmission in the access network. There are other use cases as well, but this is, I guess, the reflection to carry the signal. Now you have lower coverage area, but you also have small footprint and spectrum, and it was for higher frequencies. So it's a very good way to lower energy consumption and increase the efficiency, because you basically use reflection rather than power to spread the message. And RIS doesn't require 6G, but that's going to be the timeline, and that's where we're going to see most of the adoption.
Monica,
my time is up. Sorry.
Yeah.
Yes. So my time is up. This is my report if you want to read more, and that's all from me. Sorry.
Brilliant. Thank you so much, Monica. I appreciate that. Thank you so much. I would like to introduce Paulo Sergio Rufino from Paris, France, to present on the 6G roadmap towards ubiquitous network. Over to you, Paulo.
Thank you, Panesh. It's a pleasure being here. Let me share my screen with you. Let me know if you can see my screen.
Yes. Perfect.
Okay. So the presentation that I'm about to deliver here, it's based on this book, which I'm co-author with my PhD supervisor, Professor Emeritus Dr. Ranjit Prasad from Aarhus University. And we are here to discuss the roadmap, what we should expect from 6G. So a brief introduction. I'm a PhD research at Aarhus University and CGC, which stands for City of Global Council, which is the research center institute in Denmark, who's the president and founder is Professor Ranjit Prasad, and we study several verticals in technologies. In general, in a nutshell, the agenda of today's talk that I'm delivering here is based on the United Nations Sustainable Development Goals as one of the targets for the purpose of 6G, Society 5.0. A brief introduction, and then just going through 6G, R&D, new materials, new technologies, and future use cases. In brief, as I said, in a nutshell, so this is our department, and 6G at CGC, which is the City of Global Council, our research institute, nested inside of Aarhus University. So we have all those 12 areas of study, including vertical and horizontal industries. And future networks as part of 6G, including what you present, Ganesh, earlier, and Professor Monica Paulini, holographic type communications and green energy, sustainable energy, right? So that's part of the efficiency of 6G. But let's delve into the problems that we are facing nowadays and understand why 6G must be a human-centric network in the future. First and foremost, mobile networks, they are delivering great in terms of technology, and they are propelling our society to live and break barriers. For instance, we are starting now decreasing the number, the percentage of coverage gap. So by 2014, so to 2021, we decreased, and the coverage gap now is just 5% of the world. However, we have other challenges to connect the unconnected people around the globe, which is related to usage gap and also coverage gap. What is the usage gap? Usage gap is the issue related to people not knowing how to access internet, how to use mobile broadband technologies, or in some regions, even the language of the software systems are not adapted to those people that are using it. That's the big challenge. And we have to create ways and means to distribute and connect people across the globe. And we must remember that December last year, humanity reached 8 billion people on Earth. More than 40% of the human population does not have access to internet, which is a big problem. And those people are the most vulnerable people on the planet. If we consider COVID-19, the pandemic situation, those people that could not afford access to the internet, they could not work from home. They could not have ability to protect themselves, as all of us here in this talk today. So we have to propel and the spread of mobile broadband services, and I still need a lot of investment. And we expect that 6G take over and be omnipresent network. As Ganesh presented in the beginning, 6G is migrating the wireless technologies into the Terahertz RF spectrum. And this brings us a lot of challenges, especially because Terahertz, as we know, has bigger bandwidth. However, it's very sensitive. Of course, implementations of technologies based in ultramassive MIMO, reflect intelligent surface, optical wireless communication systems, all of this part of the systems to create a 6G vision, hyper-connected, and in which we bring people together across the globe. However, 6G not just will need to be omnipresent, working with satellites constellation, but also has as one of the objectives to inaugurate the era of the Internet of Things, where everything and everybody is fully connected. And needs to be an intelligent network. Intelligent networks being the holy grail. It's under discussion, under research and development. We have the cognitive networks. We have the success of 5G roadmap being defined in the release 17, 18, and 19. But we're still lacking a lot of things in order to deploy a full intelligent network that can predict to deliver, predict to prevent, and adjust self-healing towards end-to-end. And this is the requirement of 6G if we are aiming to have 6G as a ubiquitous network. And finally, a green energy, because that's the part of the previous talk delivered by Dr. Monica Paulin. So in terms of KPIs, as we know, 6G will be a terahertz, will be working on the terahertz spectrum, and also being able in the industrial level to provide data throughput of 1 terabit per second. Other very important part is we granted mobility to 1,000 kilometers per hour, which is very important, and latency down to 0.1 milliseconds, and low energy consumption. One of the talks here in terms of low latency, low energy consumption is based on for every 1 terabit per data transmitted, we can utilize 1 joule. That's very important. But in order to achieve this as well, so again, another important area is immersive AI, machine learning technologies, and perhaps quantum technologies, including quantum machine learning, to deploy what we need. In terms of sustainability, as I said in the beginning, in order to be human-centric, we need to look into the 17 areas provided by United Nations on Sustainable Development Goals, and the great framework provided by Japan, which is called Society 5.0. In a nutshell, if we split up all the societies in terms of history, the Society 1.0 was hunting and gathering. The Society 2.0 was agriculture. 3.0, the Industrial Revolution. So Society 4.0 is the current network society or information society, as we know, and we are migrating to the future society in which the 2 realms, the metaverse in the physical world, will encounter and will create services for the aging population. Health technologies will improve. So that's why also 6G needs to provide geolocation down to centimeter levels. This is part of one KPIs of them, of this new technology, because so e-health, non-invasive surgeries also will be exploited, will be part of the use cases. And in the end, so in terms of new materials and new technologies, we can see graphene that's being studied. So liquid antennas, all types of new algorithms for AI and machine learning. So now the European Commission just released the KPIs for AI learning in machine learning process in a data lake and a big data. So that's very important, and especially on this, we need to start looking to utilizing quantum computation, ultramassive MIMO, wireless power grid, and so on. And to finalize, that's the 6G use cases. Some of them I can give to you here: underwater communications, future space exploration, CONASENS. CONASENS stands for Integration of Communication, Navigation, Sensing, and Services. And as I said, the motto is connect the unconnect. And further literature I want to present here. So the new release book in which I participate in 6G, which is organized by Professor Ranji Prasad, Dr. Anand Prasad, Dr. Albena Mihovska, and NIDI 6G Enabling Technologies. And the next one that is coming up now in this month, 6G Visions for the Sustainable and People-Centric Future, which is organized by Professor Ranji Prasad and Professor Ruth Sophia. And finally, I want to invite all of you to participate in the 13th CONASENS workshop, which will take place this year in Tampa, Florida, US, in November 28th. Thank you so much, Ganesh. Thanks for this opportunity. And that's all. Back to you.
Brilliant, Paulo. Thank you so much. Appreciate that. Fantastic. Let us continue to the next speaker. I would like to introduce Alexander Lawrence from London, UK, to present on some commercial implications of 6G technical concepts. Over to you.
Thanks a lot, Ganesh. I really appreciate the opportunity. And thanks to Monica and Paolo as well for setting this up. Just by way of introduction, I'm Alex Lawrence, Managing Editor at 6G World. That's an online publication and news source, as a result of which I'm nowhere near the level of the various experts that we have around here. My job is not to know things and to ask questions. So what I wanted to do today was really share some of the state of general ignorance with you that I'm experiencing, and which I think might have an impact. We've seen this year that the ITU has come out with their 6G framework document. Earlier on this year, the NGMN's design requirements and suggestions came out, sort of suggesting ways that operators would like 6G to develop in terms of its technology and its use cases. And so I think we're getting a lot of clarity on what technical aspects of 6G might look like and what it might need to be or to do for different participants in the value chain. But I think there are still some questions which arise as a result of that on the commercial front. And unless we can find answers to these, then the technology solutions that we come up with might not be widely adopted or might take years to come to fruition. Essentially, what I'm thinking is, a use case is not the same as a business case, and a business case isn't the same as a business. So if we want to be ready to go, when the technology comes along, we've got to be having these conversations now as well. One key area which I think Paolo's been very right to bring up is that many governments in their 6G vision documents and so on over the last few years have been clear that their 6G should be used to reduce digital divides within and between countries. And a lot of the ideas around this seem to be related to a network of networks concept, where potentially devices can switch seamlessly between multiple access technologies, whether that's sort of non-terrestrial networks, private networks, presumably Wi-Fi for indoor coverage, possibly even mesh networking. It depends on who you talk to. But by doing all of these things, then you can get a better service continuity and hopefully allow people just to access the services that they need to access wherever they happen to be or in whatever context they are. And to be honest, that seems to me to be fairly revolutionary in and of itself. I'm in the UK, and over the course of the weekend, I was in a field trying desperately to be able to access the internet and then on a train failing to make a phone call. So if we can do that, that will be life-changing, I think, for everybody. The thing is, if we can do this, then there are a couple of big concerns. I mean, one is simply in that coverage concept with the network of networks. If we're using whatever networks are available to deliver the service, then that suggests a new type of relationship between the customer and the service provider. A typical national scale mobile operator has spent the last couple of decades competing with the others in terms of who has the best network, who has the best coverage, all this kind of thing. If all of a sudden you're just using what's there at any given moment, whether that's fixed, mobile or non-terrestrial, then all of a sudden that form of competition no longer is relevant to your customer base. So, for the telco, they're going to have to think about how they create their propositions and relate to their end customer. I mean, do we in fact end up with customers who are in fact belonging to one operator, or should they actually be paying let's say a monthly bill and dividing that up between the companies whose networks they happen to have used? I think that would be difficult, but you can see that all of a sudden these possibilities do start to open up. There could be sort of the equivalent of MDNOs to run this on behalf of the consumer, and then disintermediate all these companies that have spent billions on building out the networks. So there are some very curious corollaries there, and particularly as we're seeing now the growth in private area networks, local networks, all this kind of thing. It's going to be really interesting to see how roaming and settlement starts to work between the national scale operators, the SATCOs, and so on. As it stands at the moment, typically roaming agreements are set up at the national level between different organizations, and that can be really tricky to manage, even when there are only a handful of operators per country. So it may well be that if we're starting to see hundreds or thousands of networks opening up, either they're not going to carry external traffic, or there needs to be some way of managing traffic that belongs to customers other than those private networks. Perhaps we need to get standard terms, let's say, for roaming, sort of inbound and outbound, and how the rating, the billing, and the settlement work. And that in itself could be quite a good thing. You could start to see situations where, for example, let's say a town sets up a network to create coverage for all of their inhabitants, and they start to recoup that simply because of the fact that they don't have, let's say, direct customers themselves, but they allow any other network to roam onto theirs, and they recoup a certain amount in roaming fees. And then, as Paolo mentions, service delivery to reduce digital divides carries another implication, which is to do with affordability. So different business models are going to be required to reach them. They're in coverage, they just can't afford things. And this has been a problem forever. I think we do need to look at whether we look at public broadband or MVNOs for low-income families, for example, with subsidized services that then takes those customers out of the pool for commercial telcos, or maybe B2B2X models where the services to end users are free, but the operator receives revenues from advertisers or other service providers who want to reach this audience, such as government services and financial institutions. Or potentially we could even go to government subsidies, maybe in the form of dedicated benefits for people on low incomes, to enable a basic level of broadband access, which would then feed through to the regular commercial providers. I think we could go on, but I realize I'm kind of up to time. So these are just a few thoughts, but as you can see, there's a lot that needs to be considered alongside the technical if we're going to really make things work. And I'm looking forward to having the conversations in the next few years about what these will be. Thank you very much.
Thank you, Alex. Thank you for your clearly mentioning those points. I think those were really relevant. Thank you. I appreciate that. Now I'd like to introduce the next speaker, Vishnu Ram from Bangalore, India, to present on the artificial intelligence, machine learning, the 6G networks. Over to you, Vishnu.
Thank you so much, Ganesh, for that introduction, and thank you for the invite. I need permission to share the screen, please.
It should work now.
Right. Yes, thank you. Thank you for waiting. Okay, so today I will talk about AI/ML in 6G networks. So my name is Vishnu. Most of this work cited here is done as part of ITU AI/ML Challenge and other AI for Good initiatives. There is a link here if you need more details. Okay, so here is some background. When we talk about 6G and AI/ML, right? We go back a step and look at what we did for 5G networks. So we started this study of AI/ML in 5G networks in 2018, and we did it for about 2 to 3 years, looking at different use cases. And then we arrived at an architecture framework which describes how to integrate AI/ML frameworks into 5G networks. How did we do it? We looked at, this is an open collaborative study driven by contributions around the world, including vendors, operators, and everybody else. Universities as well. This was totally free of cost, totally open. There is no membership required to involve in such activities. We analyzed more than 30 use cases. The requirements were classified as critical, expected, optional, and so on. So this is this framework formed as a common language for managing machine learning in networks. This is Y.3172 that you see here. I won't go into details today, but I will look at the main important aspects and some of the things in relation to what you see outside in the outside world today. This is the machine learning function orchestration, MLFO. It is used for managing the different aspects of machine learning. I mean, what I'm talking about is probably 4 years back work which we have done as a background, right? But today, you know, MLOps is a very hot topic. MLOps, lot of people are working on MLOps, and 3GPP, in fact, is looking at management of machine learning in SA5 right now. There is sandbox system which looks at the experimentation, looking at the performance and the functionality of machine learning models before they are applied to the networks. There is this machine learning sandbox that you see here. And there is pipeline subsystem which describes the different nodes in the pipeline. For example, how do you collect data? How do you pre-process it? How do you train models? How do you deploy models? These are all part of the pipeline system. And finally, there are underlay networks, including 3GPP and HCGSM and different kinds of frameworks which can deploy such pipelines. Okay. So another important aspect in the form of background, what we need to look at is autonomy. Autonomy is another hot topic in the networks now. So to study autonomy in the context of, especially in the context of knowledge bases, applying machine learning, we looked at, again, a study of use cases for autonomous networks. deriving an architecture framework for autonomous networks. And this time we also did hands-on work in the form of building a proof of concept for using such concepts. There are three main things that we studied. One is the evolution, second is experimentation, and finally the adaptation, how to apply this. So you can think of it as making logic, validating logic, and applying logic, maybe using AI/ML. So the framework that you see on the right side is let me simplify it for you. Top to bottom, you look at using knowledge-based subsystems. You look at applying an autonomy engine and how to apply it to the networks, and finally applying it to the underlying networks. So important parts here are the knowledge base which you collate over a period of time, or applying machine learning, autonomy engines which allows us to apply this, evolve this over a period of time, and how to adapt it to the networks. These are the important aspects that we studied as part of this work. There are some use cases, maybe I won't go into a lot of details, but you can see a flavor of the use cases so that you know, or you understand what I'm talking about. The digital twins is an important aspect, which is looked at the platform for experimentation. I talked about the three concepts: evolution, experimentation, and adaptation in the previous slide. Experimentation is one of the important parts. Preparation of the digital twin is one of the important things that we studied. Triggering of digital twins for simulations is the next step. And finally, trigger of autonomy engine by the operator so that we can have this entire simulations setup. That is actually the last step. This allows operators and the vendors to look at some of the hypothetical questions. What if questions? What if this happens? What if a base station goes down? What if there is a sudden surge of traffic? This kind of hypothetical questions, what if questions, are answered by these kind of digital twins platforms, and they form an important part of experimentation. Okay, so with this use case, what do we do next? I mean, we derive some lessons from it. Here are some requirements. I won't go into details today, but you can see there are critical requirements which are derived as part of this. Then we look at what are the architecture components required for satisfying those requirements. So this is basically the steps that we follow. And as I told you previously, this is not only paperwork. We wrote code, build up a proof of concept, or again, collaboratively. There are universities involved. You can look, there are some references here. This work, what you see here, was led by Indian Institute of Technology, Delhi. They looked at an MEC test bed, which has a robotic hand with an edge model deployed on it, how to train this edge model for controlling the robotic hand, as you can see the robotic hand here. So that is the model that they built up, and this had a very good prize, which was done as part of a collaborative challenge. So we have a very good prize, which was given to the winner. So how do you do this? We use, as I told you, this is an open process. We call for contributions, we call for mentors, refine the use case, publish it in template, and finally review and finalize. This was done over a period of 10 months of agile editing. Okay, what are the trends in machine learning that we see as part of all these activities? So you see that there is a data-centric and model-centric view. Systematically, engineering data is used to build machine learning models, and then we are moving from unidimensional models to a multi-dimensional models. You can see on the right side. This work which you see here on the right side is actually from Arizona State University. They have given us a mix of RGB data, LiDAR data, radar, and position data, which they have collected as part of their work, so that we can train multimodal machine learning models for the future generation networks. Energy consumption, I mean, the previous speakers talked about in detail. That's an important aspect as well. And then federated learning, so that we can avoid some of the costs involved in machine learning, including privacy and transfer of data. What would be some of the some of the applications. So one is the multimodal beam prediction. This was a very important and very interesting and very popular challenge which we did. As I told you about the data in the previous slide. Another thing is the graph neural networks, how to apply graph neural networks so that we can have these digital twins, how to train graph neural network models as digital twins. So they behave as digital twins. That's actually quite an interesting problem statement which we had. Federated traffic prediction models mapped to my previous slide. So this one is another interesting topic which looked at privacy and distribution of models. This included real data from a network. So what would be going forward for 6G? There are advances both in AI/ML and in the networks, and there is availability of data which I talked to you about from our work in the AI for Good. There is a lot of network data which we have collected and made publicly available. And lastly, this is not individual work. I mean, this is building up an open community is quite important for us. So collaborations with academia and industry is called for. The generative AI is coming.
The time is
Thank
over.
you. Thank you so much. So I will maybe look at some of the open data sets. These are available here. There is a link available here as well. You can look at those links for great details. Thank you so much.
So much of information, very informative, brilliant. Thank you so much, Vishnu. I appreciate that. Next speaker. Let me introduce Professor Dr. Gilberto Bernardinelli from Denmark to present INEX subnetworks for short-range extreme communications. Over to you, Prof.
Yes, thanks, Ganesh. Hope you can see my screen.
Yes, Prof.
Yes. Okay. So thanks. So as Ganesh said, my name is Gilberto Berardinelli from Aalborg University in Denmark, and it is my pleasure to give this short talk on INEX subnetwork for short-range extreme communication. So just to give a bit of background, we know that wireless communications have become more and more pervasive in the last decade, and this trend is expected to continue in the coming years. If we look at cellular, we know that 5G has introduced the concept of ultra-reliable, low-latency communication. So using wireless not only for best effort high data rate, but also for delivering maybe little amount of data, but with very high reliability and constrained latencies. And this the trend towards more and more demanding use cases is expected to continue with 6G, as we have already seen in some of the previous presentations. So with 6G, we may target requirements that are like multi-gigabit per second, but also significantly lower latencies than 5G, like fraction of milliseconds, and even a higher reliability. It is common understanding that if we want to achieve these high performance requirements, those cannot be achieved over a wide area network, but we need to bring the infrastructure very close to the devices demanding those applications. So we need to go local, we need high performance short range communication, and we can use what we call INEX subnetworks that are also part of the European Vision for 6G network ecosystem, and that I will be introducing now in this short presentation. So what are INEX subnetworks? As previous speakers have already highlighted, 6G is expected to take the form of a network of networks. So integrating networks having a very diverse capabilities in terms of operational range, spectrum, services, ranging from macro, micro, pico networks up to network of drones, non-terrestrial networks, and so forth. INEX subnetworks are expected to be located at the very end of this network of networks, to provide very localized and high performance connectivity in entities like robots, vehicles, production modules, classrooms, and so forth. For example, industrial subnetworks can be used for supporting wirelessly fast closed loop controls in robot, like force control. In-vehicle subnetworks can replace automotive Ethernet for motor control, braking, but also for advanced driver assistance systems. In classrooms, in-room subnetworks can be used for education, like extended reality, immersive extended reality applications for education purposes. And we can even have in-body subnetworks, so having sensors and actuators in the human body wirelessly connected that can be used for life-critical services, like, for example, heartbeat control or haptic muscle control in disabled patients. So applications and use cases of those in-X subnetworks can be very diverse. A common characteristic is that performance requirements might be significantly more demanding than what expected, what's supported by current radio technologies, and this is why innovation is needed. Also, another characteristic is that by default, by design, those subnetworks can spontaneously become very dense, like, for example, cars in a congested road. And this means that interference is a very major problem we need to deal with in our radio design. A third characteristic is that those subnetworks might be able to operate standalone, because they are supporting, in some cases, life-critical services that cannot be interrupted at any time. But on the other side, they are part of a larger landscape, so they can benefit of the support of a broader 6G network and infrastructure, for example, providing a unified authorization framework, but also it can aid managing the radio, spectrum, and the computational resources. So given this, I would like to give you a very quick introduction of what are the technology components that we are researching on when coming to subnetworks. So as I said, subnetworks is about connectivities in entities like robots, vehicles, classrooms, and so forth. Within each of these entities, we can have one or more subnetworks, where a subnetwork can consist of an access point serving a number of devices. Those devices can be low-cost devices like sensors, actuators, but also cameras, for example, in the case of ADAS sensors. Also, within a subnetwork, we can have a RIS. So Monica has already introduced reflective intelligent surfaces earlier. So those RIS can be placed, for example, nearby a production module or even within a car to help steering the signal in the desired direction. Given this, it is important to characterize the short-range radio propagation within those entities. So we are looking into different spectra here. So as we know, we are quite open in terms of 6G spectra, can be below 20 gigahertz, but also millimeter wave and the sub-Terahertz bands. Regarding a physical layer, we are looking into beamforming, but also beam focusing solution. So steering the beams not only in the angular domain, but also the depth domain, leveraging the near field propagation characteristics, and enhancement for the RIS. Regarding medium access control, it is important to look into ultra-reliable low-latency communication enablers beyond 5G. We know that 5G can support 0.5 millisecond latencies. Here, we may need to go significantly beyond that. So there is room for some innovation there. But also different type of schedulers like flexible full duplex schedulers or predictive schedulers. Within a subnetwork, we may have more than one access point, which means that those access points can be used for providing redundant radio links, so improving the reliability of the shadow of the links. Also, we may have more than one subnetwork within a same entity, and therefore operations and traffic need to be managed among the subnetworks operating in the same entity. Also, subnetworks might need to be robust to jamming attacks, especially those that are supporting life-critical services, and this can be done at the physical layer, designing the physical layer to be robust to jamming attacks, but also let's say designing a solution for detecting and mitigating the jammers. Everything I said so far referred to a single entity. As I said, entities might be very dense, like vehicles in a congested road, and therefore they may create some strong mutual interference. So it is important to look into radio resource management, and this should be distributed solutions for radio resource management. So some networks should be able to autonomously select frequencies, power, beamforming vector, and so on, such that the mutual interference is minimized. Also, as I mentioned earlier, some networks are part of a larger infrastructure, so we may rely on the 6G, on the connection to the 6G network that can help managing radio resources of the subnetworks in its coverage area. And the 6G network can be connected to a central cloud, so can take care of sharing traffic, spectrum, but also computational resources between some network and the broader network. So this is a little bit the landscape that we are looking at when looking at some networks. So entities that should be able to be smart and operate standalone, but they can leverage the capability of being a part of a larger 6G ecosystem. Before closing, I just want to mention that we have a European project fully focused on in-access subnetworks with the goal of designing technology components for subnetworks. This project belongs to the Smart Network and Service Joint Undertaking Work Program. It started recently in March, so we are still at the early phase. We have a nice consortium with a good blend of expertise of industry and academia, including very big players like Apple, Sony, Nokia, Bosch, Interdigital, and Keysight. So if you're interested, you can look at the website, subscribe to the newsletter to be updated on the progress on our project on in-access subnetworks. This is all from my side. Thanks for your attention, and feel free of reaching out for any question and clarification. Thanks.
Excellent. Thank you so much, Professor. I appreciate that. Now, moving on, let me introduce the next speaker, Dr. Uttara Sawan from Texas, USA, to present on the 6G-enabled massive IoT networks. Over to you, Dr. Uttara. I can't hear you, Dr. Uttara. Are you there, Dr. Uttara?
I'm here, yes.
Yeah, okay.
Unmuted, okay. Thank you, Ganesh. Smart services based on the Internet of Things are gaining considerable popularity due to the increasing demands of wireless networks. Although 5G networks show great potential to support numerous IoT applications, it is not quite adequate to meet the complete requirements of the new smart applications. Therefore, there is an increasing demand for envisioning the 6G wireless communication systems to overcome major limitations posed by the existing 5G networks. Hi, my name is Uttara Sawan, and today we will explore 6G IoT with respect to requirements, technologies, applications, and challenges. This is the agenda for today's presentation. The fast growth of automated and intelligent IoT networks is likely to exceed the current capabilities provided by 5G wireless systems. Now, 6G is expected to provide an entirely new service quality and enhance user experience in the current IoT system due to its superior features such as ultra-low latency communication, high throughput, satellite-based customer services, massive and autonomous networks. In that context, Finland's 6th Genesis project, Nokia's Hexa-X, South Korea's K-Network, and United States' NextG Alliance are examples of pioneer 6G projects launched to promote 6G research. Now, to fully realize the 2030 information society of full intelligence, massive device connectivity and coverage, data-driven services and autonomous systems, 6G IoT will need more stringent requirements over its 5G IoT counterpart, with 1, massive IoT connectivity, 2, massive ultra-reliable low-latency IoT communication, 3, improved IoT communication protocols, 4, extended IoT coverage, 5, next-generation IoT devices. The fundamental technologies that are envisioned to enable 6G IoT networks are as follows. First is edge intelligence, which occurs when AI functionality is extended to the network edge to provide fast and reliable AI data processing at the edge devices. Now, similar to edge computing, fog computing offloads computation to the fog nodes, and when combined with AI, will result in fog intelligence. Additionally, as we have seen earlier, federated learning, a distributed AI approach for privacy and cooperation of massive IoT devices, is also being considered. Second, reconfigurable intelligent surfaces. RIS, we have seen the previous speaker speak about it, consists of arrays of passive scattering elements with artificial planar structures, where each element reflects the impinging electromagnetic waves in a software-defined manner. The reconfigurability makes the RISs a promising solution to enable smart radio environments beneficial to 6G IoT applications. Third, space, air, ground, underwater communication form a cell-free 4-tier large dimensional communication network for 6G IoT. LEO, MEO, GEO, UAVs, submarines are considered in this category. Terahertz communication, 0.1 to 10 terahertz band is promising to fulfill 6G IoT requirements with high throughput of 100 plus Gbps. Case studies for user localization, balanced performance in vehicular IoT communications have been carried out for this purpose. Next is massive ultra-reliable low-latency communication technology, which can be applied in remote healthcare and automated manufacturing with a very, very high reliability and block error rate of less than 10 to the power of -5. Finally, blockchain, an emerging disruptive technology to offer privacy and security for 6G IoT applications, where every IoT device is a node controlling and authorizing data in the blockchain, such as UAVs and IoT application in smart healthcare. Applications. In this context, 6G will be designed to realize a plethora of new IoT applications by satisfying stringent network demands. First is 6G healthcare IoT. MUR LLC and Terahertz Communications are combined to realize applications such as remote doctors, remote diagnosis, and connected ambulances. Machine learning techniques such as Bayesian classifier, logistic regression, and decision tree can be utilized for analyzing the historical health records of stroke outpatients using wearables. Multi-sensory applications such as remote surgery combined with AR, VR, or holographic communications and wireless brain-computer interfaces will truly constitute immersive services for 6G. Second is 6G for vehicular IoT. This exploits massive machine type communications to enable V2X connectivity for transmission of short vehicular information payload across large number of vehicles without human interaction. Edge intelligence functions along with machine learning are integrated into the roadside units that are responsible for estimation of traffic volume, weather forecast based on aggregation of local information from the vehicles. Next up is 6G for UAVs, which considers a cell-free UAV network for 6G IoT focused on UAV flight optimization. Now, given the popularity of cluster IoT terminals, a terminal clustering strategy is adopted based on the NOMA communications, which allows UAV acting as a mobile relays to transmit radio signals to the IoT terminals. Next up is 6G for satellite IoT. We all know the LEO system is more preferred due to its lower orbital height and useful features to support IoT connectivity. Satellite communications can also be integrated with the RIS technology to enhance transmit power. Now, energy management and spectrum scarcity are, however, the challenges facing 6G SIoT. They can still be managed using NOMA and cognitive radio technologies. Finally, 6G for industrial IoT. Intelligent agriculture employs blockchain-based 6G IIoT network using AI techniques for optimizing processes and blockchain for securing production and logistics. Additionally, mining industry is also projected to benefit from 6G IoT with massive, ultra-reliable, low-latency communications. But 6G IoT network comes with a certain set of challenges. The diversity of IoT devices and access mechanisms pose certain security and privacy risk to the network. Personal IoT network PIN aspects such as PIN authentication and authorization with 5G core work item study has been included in 3GPP release 18 and further into release 19. The energy efficiency is managed by exploiting energy harvesting, where we can harvest power from ambient environments such as wind power, solar power, vibration power, thermal power. One example is, which is not quite using 5G technology or not even close to 6G, but one which uses Bluetooth, low energy, which is Deloitte IoT Pixel. Do check it out. It's pretty neat commercial model. Next up is the hardware constraints for IoT devices. We all know that certain IoT wearable sensors and mobile devices cannot meet the computational requirements. So they pose hardware constraints, memory and power constraints for further processing. And finally, introduction of the vertical 6G IoT use cases incurs a major architectural changes to the current mobile networks, also leads to significant standardization effort. Some of these work study items I have quoted in at the bottom left of the slide, and these are ongoing study items for 6G IoT aspects.
Uttara, the time is over.
Okay. Finally, in conclusion, 6G will transform the current IoT network infrastructures and bring new levels of service quality and user experience in future IoT applications. Thank you for listening, and over to you, Ganesh.
Brilliant. Thank you for a great explanation, Dr. Uttara. Appreciate it. Let me introduce the next speaker, Professor Dr. Ranjan Singh from NTU Singapore, to present on Terahertz 6G communications. Over to you. Yes.
Hello, everyone. So I would like to share with you some of the ongoing efforts on developing the Terahertz 6G communication hardware in my lab. And the approach that I take is mainly photonics. Now, as this audience already know, that 6G is being believed or envisioned to be a merger of the physical, digital, and the biological world, where the network will have a sixth sense and the network will be able to anticipate our needs in such a way that it will augment human productivity. For example, it's envisioned that all of us will have a digital phone. Now, one of the first devices that we did was in 2020, where we propagated data using terahertz carriers at 11 gigabits per second on a silicon chip, about a centimeter long. With respect to this data rate, we are at about 327 Gbps right now. So there has been a lot of excitement and developments in terms of coming up with the technology that would allow propagation of terahertz waves on a chip and then beaming it into free space. This is the folks that do all the work and the funding agency that I'm thankful to. Now, this picture has been shown, I think, several times. What I would like to highlight here is that 8 to 10 years from now, when we are looking at the onset of 6G, then we need to develop devices above 100 gigahertz frequency. So the peak data rate will go up to 100 Gbps, and the carrier frequency will go beyond 100 gigahertz, and that's the real noise of terahertz frequency, which sits between microwaves and infrared in the electromagnetic spectrum. Now, electronics seems to have some fundamental limitations in terms of transistor cutoff frequencies. The photonics also seems to have some limitations in terms of the band gap of semiconductors and the process of population inversion and lasing. That's not possible at this frequency and temperature. So we need to come up with devices that can somehow complement the lossy electronics at terahertz, and that's what we do via photonic devices. These are some calculations based on the Shannon theorem, where if we want to see a fiber-like speeds in free space, then the only way is to go to terahertz waves. So, and then this whole spectrum between 100 gigahertz to 50 terahertz can be tapped. Of course, it's going to be very challenging. Every 100 gigahertz of bandwidth that you add, you need to come up with some new devices, new technologies. So this is not going to be easy practically. But then when you look at the tower capacity numbers, you could go up to hundreds of terabits per second of wireless communication. Of course, we can argue about the range and whether this will be a reality or not. But the message really is that if we want to see fiber-like speeds in wireless, the only way is terahertz carrier waves. Here comes the bad news, where you can see that the attenuation on the y-axis is high, especially as you go beyond 500 gigahertz. So this is the regime that we are trying to design our devices. So the low attenuation regime, the peaks are high attenuation points. So, I mean, even this regime here offers a huge bandwidth, and it should be possible to hit terabit per second of data speeds. So in terms of carrier aggregation picture, terahertz is not at the range, and you can see terahertz ellipse is the smallest. So, and then comes the millimeter waves. Terahertz is the sub-millimeter waves. And then all the other generations. Not going to be a standalone technology, it's just a complementing technology, and it's going to work in conjunction with all the other carriers that's out there. Just that it has revolutionary potential in terms of decongesting the network. Now, one of the recent demonstrations done by a group in Northeastern University and NASA is this point-to-point line-of-sight communication, 2 kilometers, using gallium arsenide-based Schottky diodes and power amplifiers. So they managed to generate 200 milliwatt of sub-terahertz power, and I think carrier frequency is about 270 of probably 25 gigahertz, and they use a high gain antenna. So this was a demonstration that yes, terahertz can be used for a larger distance communication, although just point to point and line of sight. If we want to fix the problem of attenuation in free space, we need to fix the problem at the chip level. And terahertz as a carrier is not just a solution for wireless, but also for interconnect applications to connect two different chips or to make connections within the chip itself. As you can see here, the connection between the CPU and the RAM. This copper wire, if we replace with a silicon interconnect, then copper, where the figure of merit drops by 3 orders of magnitude due to Joule heating, that will not happen if we have a silicon interconnect. So the y-axis that you see here is basically the figure of merit about how much data you can pack and how much energy is spent in sending 1 bit of data across this interconnect. So some calculations that we did is right here with silicon. You can see that we can go all the way up to the band gap of silicon, and the losses can be controlled. Now the interconnect here that I'm showing you has some sharp bands. So we have some technology through which we can flow data through sharp bands, and there will be no losses involved. And one of the demonstrations that we did is here. You can see a chip with 10 sharp bands. And when you look at the transmission through straight and the 10 sharp band is right here. Of course, it has a bandwidth limitation of about 30 gigahertz. But then using this particular technology, we also modulated Terahertz carrier with the uncompressed video data that I would like to play here. And the device is a part of a wireless network, as you can see here. So here is the device with the bands, and the video data is being sent through this device. You could try to block the network with a paper that is transparent paper, and then you come in with a metallic sheet, and then that can block the Terahertz radiation, and the ultra high definition video in the background disappears. So it's just a proof of concept demonstration that our device could be a part of a wireless network. We further improved the interconnect speed all the way up to 160 Gbps by using rich amplitude modulation. Like you can see here, this is the performance of a different device. This is without the device, which is the reference. And we did some more demonstrations of diplexer, which is a combination of multiplexer and demultiplexer. I don't want to go into the details of this, but we are regularly being able to 100 gigabits per second. We've also done some reformers and some antennas, with a gain of about 14 to 20 dB. And what I would like to point out is that in this chip, there are 45 sharp bands, and we still are being able to couple the data in, split it into 16 different parts, and form a phase array so that you get beamforming in 2 different directions. And same here, it's a waveguide come on antenna that can have directional emission. So this is the last technical slide that I have. Basically, we recently did a wireless communication over a distance of about 8 centimeters at 100 Gbps, and we plan to go further. Now, the only limitation here is the source power. The source power that we have here is about 0.5 milliwatt. So if we can ramp that up, this distance could be ramped up to about a kilometer or so. These are some open problems in this community. There are a lot of electronics and for running devices that has to be developed for 6G terabit per second communication to happen. And this is more of a futuristic thing. I would like to leave you with this vision here and some activities that I have in my group and also collaborating with industry partners. Thank you very much for your attention.
That was brilliant, Professor Dr. Anjan. Thank you so much. This is really well informed. Thank you so much. Let me introduce the next speaker, Dr. Anand Prasad from Tokyo, Japan, to present on considering security in the new era. Over to you, Dr. Anand.
Thank you very much, Ganesh, and thank you for inviting me and all of you here. Can you hear me well?
Yes, Doctor.
All right, and I hope you can see my slide as well.
Yes.
Good. Hey, again, appreciate your time. So, and having me here. My presentation is about 6G and security. I'm calling it the new era. And I'm from Deloitte Tomatsu Cyber. A little bit about myself, just to give an indication. I have over 25 years of experience in security space, as it is called, cybersecurity as well. And I have worked in standards. I was chairing 3GPP SA3 working group when 5G happened. I have worked in standards, as I said, with regulators as well, in terms of deploying and developing network from scratch and bringing security to them to operations. And also now had my own company and now working in Deloitte as a partner. Now, this is here my story starts. A couple of slides only. We have 10 minutes. It's quite a big topic to talk about 6G security. But talking about generations and how things happened, a picture I made a while back, actually, and you can see the data rates based, because initially that's how we used to talk about things. And as we move towards 4G, what happened in that time, I was writing the specifications as well with my friends there in 3GPP. We started off as usual with a lot of space for data rates. And then as we move ahead with the standards and in time, we developed new things in specifications. You came with the IoT-based services. You came with solutions that did not require your connectivity to the core network and still give some kind of mission critical services and things like that, proximity-based services and stuff like that. The point is, all these things adds together, all these technologies and services developed in a generation added together to the next one, which was then the 5G. So the point being that when we talk about any new generation, then that new generation gets developed with new ideas as time passes. And those new things together then forms part of one common standard as a next generation that's coming up. So 5G doesn't have as much enhancements as 4G had, but whatever it was will go to 6G. This is just setting the base. And that's how I have seen standards working over the decades. Now, couple of things that will be unique and stays is that will be there and stays over generations are kind of presented here. If I had time, I could spend an hour on talking about all these points and security of each of these points, but let me just touch them very quickly. I'll touch, of course, from the security credentials part. I'm talking about security here. So we have talked about UICC. That's where all the security lies, and then we're talking about also eSIM today. But then as we move ahead, we'll see enhancement in terms of storage and new kinds of solutions. And that could also mean the kind of key or credentials provided. End devices, we will see quite short-lived end devices as well as more and more of embedded coming up. Services, I have to say I should have mentioned the blue ones text over here that is there is something I have added in addition to what was there in 5G. And we'll see as you go towards 6G, we'll see much more personalized services, which again has implications on the network. We'll see technologies, we'll see services coming very fast as well, based on technology and different kind of solutions out there. We are talking about, for example, ChatGPT and stuff like that kind of things come today already, but also software development pace being fast. Business side as well, because of these things on the right that I discussed, there'll be rapid changes, which will again have implications on the 6G network and services that can be provided. And then lower side, instead of taking too much time, we'll see newer and newer technologies working together. And then these will also have the implications on the 6G security. One specific point though, because we're talking about security, is that we probably will also see enhancement in the roaming side. Yeah, which also has impacts on security and also fraud aspects. And another point that we should not forget is the generation change, how people are using mobile communication and the coverage going to say 8 billion. Yeah, a very important point. Don't forget, don't just go about, wow, we have all these enhanced and beautiful services, but we need coverage and we need services for all human beings on the planet, not only the things that I already talked. Yeah? Which has its own implications in every sense, including security and privacy. Now, when we talk about 6G, these are some of my points here and some of the implications on security. I'll look at my time as well. So a couple of points. One thing, legacy technologies, they'll be there. Any new technology will have backward compatibility. And that means that you will have to have security that takes care of that compatibility. You always had from 5G towards 4G, 4G, 3G, and things like that, even 5G to 3G. What also happens at every standards when we start standardizing, we have some dreams, yeah, but we don't fulfill those dreams in that generation. And those dreams are always taken over to the next generation. So you can look at some of the 5G dreams, even 4G, and these might appear in 6G. And then we'll take care of known vulnerabilities in 6G. Like in 5G, we took care of integrity protection or privacy aspects and things like that. Then there's always use cases. Security is based on where it will be used. Some people talked about digital twin, for example, mixed reality experiences or localization. All these bring security requirements, and then those things will be also result into security in the 6G era. Yeah. Then there'll be new technologies, of course. Yeah, let's not forget that. We talked about quantum computing, AI. We discussed about DLT as well. We talk and then AI. I'm just putting it there, but generative AI as well, and all this stuff. All these things have security implications as well. You learn something, the generative AI, and can attack, for example, can also protect. Quantum computing has a similar implication. The combination of all this, you can just dream about the impact. Yeah. And then there's societal factors as well. Sustainability requiring, of course, that we use less energy, but then what is the impact of that on security? Privacy requirements is going up and up throughout the world, actually. And that also has security implication and geopolitics too, without going into details of that. Then there is a security enhancements by itself that will come into the next generation. We will see crypto algorithm enhancements. Without saying that, quantum computing is having its fun with that part, and we'll have that. We'll also have new security protocols coming up. And then the long-term key that we are talking about, I touched with the same aspect in earlier slide, will also be changing and impacting the system. And then because of that key derivation as well. Ganesh, I guess I take 1 or 2 more minutes. So this is about generational changes and security, how it changed. I can spend too much time here, but just very quickly, what you should expect also in 6G, that we will touch again authentication and key agreement and how that is done, and allow many other ways to come. Key derivation and then management will also change. New things will come that side as well. Yeah, and then roaming aspects that I said briefly earlier. So finally, this is my last slide. Couple of things to keep in mind. Standards, we'll see specifically all the things I mentioned earlier, but we should also think about the short-lived networks and their impacts on security coming in standards. Industry forums and individual organizations, their recommendation is that look at best practices and take care of them properly. And regulators do play a very important role while taking care of security and business going hand in hand, as well as architecture aspects. So with that, in this short time, a lot of input. I hope this is of help to everyone. Thank you for your time. I appreciate that.
Excellent, Dr. Anand. Thank you so much. That was very nice of you. Now, moving on To the next speaker, I would like to introduce Professor Dr. Paresh Saxena from Hyderabad, India, to present on the MEC-enabled NTNs for 6G.
Yeah, hi, Ganesh. I'll share my screen now.
Yes.
Can you hear me and is my screen visible?
Yes, Prof.
Okay. So first of all, thank you for inviting me. I will be speaking on MEC-enabled NTNs for 6G. And my name is Paresh Saxena. I'm from Department of Computer Science from BITS Pilani, India. Just a small introduction. BITS Pilani has 3 campuses in India, and I'm from the South from Hyderabad campus. I'm here leading a team of researchers who are working on the applications of deep reinforcement learning on different domains. And one of the important domains that we consider is about MECs for NTN. Moving forward, just one slide to show that holistically, where you can see on the top side, if you have data moved to the cloud for any processing with certain delays at certain points from the device to the cloud center, you may obtain around 25 to 30 milliseconds of latency. On the other hand, if you bring processing to the edge, it can reduce the latency of up to 20 to 12 milliseconds. Of course, these numbers can change on technologies that have been used. The latency, as you can see in this example, can be reduced drastically, and hence just the motivation of using MECs. And MECs, which refers to multi-axis edge computing, is not it does not consider edge only at the mobile network, but edge can be considered for any devices that are now being used for different communications. The scope of MECs covers certain benefits that it can provide, and
Professor Paresh, are you
sorry,
there?
there was some. So flexibility of, yes, can you hear me?
Yes.
Sorry, there might be some. So yeah, I was discussing the scope of MECs, where MECs provide certain benefits, including the reduced efficiency, flexibility that it provides, where where you do not need to send all the data to the cloud, and the enhanced security, which gives you the freedom of processing data locally rather than transmitting over it to the cloud. In addition to different benefits, you can have several services, including caching, communications, and computations. And there exist several use cases ranging from healthcare to agriculture, to industry, to transportation, wherever you would like to reduce latency, wherever you would like to have computation devices, more computation devices, and wherever you would like to have reliable communications, you have another slide just to show the market growth. This is taken from the report from 2022, where you can see that market size value in 2022 was 11.24 billion US dollars, and expected to be around 150 to 160 billion US dollars, with a cumulative growth rate of around 39 to 40%. So a lot of things have been happening at the MEC site with respect to the standardization, where you have 3GPP release 17, providing several specification, and also ETC, ATSI that have several standards with respect to the APIs, different requirements, different use cases for MECs. So MECs was one component of my talk. The another component is NTNs, where NTNs, non-terrestrial networks, including all the non-terrestrial networking systems, UAV, apps, and of course, a hot research area since several years now, where you have different use cases, specifically focusing on 6G. It can provide support in several network and computing convergence, several integrated services, and for enhanced ubiquitous. The growth that shows that the market size of NTS is expected to be around $53 billion by 2030. And similarly for satellite, you have the expected market size is going to be around 160 USD, 160 billion USD, with the cumulative growth rate for both UAVs for more than 9. So with this in mind, and of course, that standardization activities, you have 15, which talks about study on NR to support NTNs, then release 16, providing solutions for NTNs, then release 17, which talks about NR to support NTNs, and also the study on NB-IoT and its support for NTN. And then there is also release 18, which provide guidelines for extraterrestrial 5G systems. So given the motivation of MECs and NTNs, what we have is now a hot topic of research, which is MEC-enabled NTNs, where you can have the edge computing device either at the terrestrial node, which have been focus of research in the last 10 years. But in addition, you can also have the edge computing device at UAVs or at satellites, or at the hybrid. You can also use a combination of UAVs and satellites to enable edge computation at for the non-terrestrial networking systems. So just to think, yeah, I have a few more minutes. So few key barriers for MEC-enabled NTNs are resource allocation. It's important to understand how you would allocate the resources, how much the devices should process, how much they should offload. Should the offloading be binary, or should the offloading be based on certain decisions? Trajectory planning, resource deployment are some of the key barriers for the deployment of MEC-enabled NTNs, with, of course, the overall objective or the motive of decreasing energy consumption, decreasing latency to provide good coverage and connectivity. And my final slide on the challenges and opportunities that we also presented in one of the Xavier journal is regarding the emerging use cases with respect to MEC-enabled NTNs and their use in the smart cities. There have been some of the projects which are focusing on the use of MECs for the pandemic management, for smart agriculture, for Industry 5.0. There are several research directions, possible use of multipath networking and the multipath networking technologies to enhance the bandwidth for the content delivery, and for decide the pricing strategies to offload the computation from the devices to the edge. Some of the challenges that we have from the system point of view is the onboard processing, additional onboard processing, which are critical in the case of UAVs, for example, to address the dynamic environment and the dynamic network conditions that exist when we talk about the NTN systems and the different training locations that we have. And finally, the key potentials are the information dissemination, fast information dissemination, continuous connectivity due to these edge devices, possible relaying and the communication of information, and of course, a reliable communication where the enhanced security can also be added, where you can process the data locally. With this, thank you, Kanish, for inviting me, and thank you for this opportunity.
Thank you so much, Professor Dr. Paresh. I really appreciate for your input. Now, let me introduce the last speaker, Dr. Mike Wang from Taoyuan City, Taiwan, to present on MIMO for 6G. Over to you, Dr. Mike.
Hi, can you see my screen?
Yes, doctor.
Okay, thank you. Okay, so I'm Ethan Wang, or you can call me Mike, and I am the founder of Renitech, and today's topic is about Mesh MIMO for 6G. Okay, so I will provide a self-introduction of me first, and then we introduce RainTech, and also we share my perspective on machine MIMO for 6G. And I am Mike Wang, and I am a PhD from the National Taiwan University, and I have worked in the IC design company, MediaTek, and also the telecom operator, Chunghwa Telecom, and the system manufacturer, EaserTech, and we provide a 5G millimeter wave small cell. And I also have some R&D team management experience. Okay, and RainTech is an IC design company and headquartered in Taiwan. And we focus on providing the most energy saving and cost-effective base station chip solutions to wireless networks, such as the 5G and the 6G, and also the satellite communications. And we provide baseband chips for the Orange radio unit. And for the satellite communications, we provide our chips for the such as the LEO satellites or some ground stations. Okay, then we talk about machine MIMO. And we know that there are lots of benefits of machine MIMO, such as and we introduce the machine MIMO is a technology that the base station will have a lot of antennas on the base station. And accompanied with the baseband signal processing, it can provide the following benefits. The first is that they can provide, they can serve more users simultaneously, and also it's a green technology because it can save the transmit power of both the base station and the cell phones by the factor of n, and n is the number of base station antennas, so it can provide the energy saving. And also it is equivalent to increase the coverage, and the machine MIMO coverage should better than the 4G MIMO system. And also it provides a near optimal performance. Okay, so about the antenna number, we know the 4G, the MIMO for 4G is up to 8 antennas, and currently 5G uses the machine MIMO, and it's up to 64 antennas. And for the 6G, maybe it may up to about 500 antennas. It's possible. Although the transmit power can be reduced, but the circuit power is increased. And we know that the total power consumption is the transmit power and also the circuit power. So if the circuit power is increased, the energy saving may need to be improved. So we have some directions to achieve energy saving for 6G. The first one, of course, we try to increase the antenna number for the base stations. And also we may try to reduce the power consumption of circuits, such as the digital circuits. For example, we may use the better semiconductor wafer processing. For example, we use the smaller nanometer processing to build the chips. It may reduce the power consumptions on the digital circuits. And another direction is to reduce the power consumption on the analog circuits, such as the RF components. So I think that we need to improve the RF energy efficiency if we want to apply the machine MIMO to 6G. Okay, so we try to answer the question: is ultra machine MIMO possible for 6G? We think it is possible, but we need to improve the power consumptions on the circuits to achieve the energy saving. Okay, so it's my quick talk. And those are the reference to prove that the machine MIMO can theoretically reduce the transmit power by the factor of n. And this is my contact information. Okay, thank you.
Brilliant. Thank you, Dr. Mike. Thank you so much. Really appreciate that. Let's have like, say, for about 10 minutes of a quick Q&A session, a brainstorm, just to try to understand about the happenings in the research study of the 6G. Maybe I can start first. based from my understanding, what I've observed so far is that, just one second, is my video is on? Yes. Okay. So I realized that in terms of the 5G deployment today, what are the drawbacks currently? What I have seen so far is in terms of the delay of 5G standalone deployment massively around the globe. There's a lot of still relying on the non-standalone. The mobile operators are still considering moving towards the standalone. So that can be a drawback to enjoy the experience of the real 5G use cases. Number two, the usage of the millimeter wave. There's still limited use cases in terms of the 28 gigahertz. Not all mobile operators or non-mobile operators are exploring the millimeter wave 28 gigahertz. Number three, in terms of the IoT, number of sensors, connectors, this can be prone to the security. Are there real security measures have been taken? Number four, in terms of the indoor solutions for 5G, for the outdoor coverage, perfectly working very well, but for the indoor, there are still a lot of challenges. I'm not sure. There can be many reasons, either not enough of spectrum, or it can be some issues with the owner of the indoor, or whether they don't have a proper in-building solution for the 5G particularly, so on and so forth. So taking some of these issues that is being present in the 5G, are there any kind of studies being taken towards to the 6G, particularly in discussing either the 3GPP body or any other GSME bodies or any other university research? What kind of challenges that you really foresee in terms of the research in the 6G? This is my, quick questions. Anyone can able to address this?
I can have a go if you like. I mean, it's not directly to do with university research, but I think you're right. There have been all of these problems, between the specifications and the deployments of 5G, and so we have been hearing loud and clear this year from the telcos that we can't go through that cycle again. So just a few months ago, I was talking with some operators who were suggesting that if at all possible, having something that was software based and therefore would be capable of just being layered on top of 5G and 5G advanced as and where it's necessary. Maybe defining 6G not necessarily purely in terms of radio, but as a set of capabilities that then you can try in the network and take out accordingly, which would save a great deal of money in terms of that deployment. And that would make it much more possible for them to do. And I think experimentation like that and taking some different concepts as to what 6G might be or how it might be deployed is going to be really helpful in terms of moving things forward and accelerating that that pace of deployment.
Anyone wants to add anything?
Maybe I can just add two words. I think, as just said by Alex, maybe I'm repeating his words actually. One is the technology readiness, of course, and the other is the monetization part, as was being said. I mean, clarity on what kind of services can be brought, because deployment of network is very expensive. Running them is also extremely expensive. So, what are the new ways to monetize with the technology that will help, of course. And you were talking about research on that. I'm not sure. Maybe research can be done on that and studies can be done on that. But certainly standards, they get requirement from marketing side, could be more focused, and then that can help. standards to have more focused kind of specifications coming out.
In terms of the opportunity in the 6G, do you think the IoT will be the best segment that needs to be focused on from the 6G point of view, or any other segments will take off in coming 2028? What's your guess, wild guess? What do you think?
Let me quickly add. I think that the dreams presented in 5G for different kind of IoT solutions haven't been fulfilled. And certainly, so variety of these IoT-based solutions, and which adds to services as well, not only end devices and network. Certainly, that will be there. And then enhanced technologies, as I was mentioning, which will lead to different new opportunities that will also play a key role as well, without repeating all the things already said earlier.
Because I noticed most recently the Leo is getting so much kind of a trendy. There were quite a number of what they call IoT satellite companies that offering the IoT over the Leo, and and the NTN IoT is getting more trendy nowadays. But obviously there is some sort of a drawbacks in terms of the capacity and also the speed, the latency. You cannot be as good as the terrestrial. But in terms of the wider coverage, yes, it can cover much more bigger coverage. And maybe for IoT, you need just few kilobits per second. Then I'm sure that it will work very well. Obviously, there will be some studies in the 6G as well, how to maximize the capacity, perhaps in the IoT segment. Nevertheless, the Starlink is getting much more popular on the Leo, and obviously the Starlink couldn't able to meet the 5G's performance, but obviously Starlink is studying. They have actually sent the V2 second generation. It's much more enhanced performance for the broader coverage, mainly in terms of voice calls, low kilobits per second. So I think there is pro and cons in terms of the NTN as well. So yeah, anyone have any questions, or anyone wants to add any remarks here?
Maybe on your satellite communication, the people should take care of security also from the very beginning.
Yes.
I'll stop there. Maybe someone else has something.
I was thinking also the penetration of this IoT solution, especially for industrial IoT, probably has been a little bit slower than foreseen at the beginning of the 5G, especially for the introduction of all the 5G private network and so on. It seems it has been a little bit slower than expected. And now we are already thinking, okay, what will be coming next, how to further empower verticals with more and more advancing capabilities and so on. So could be that 6G will realize the vision of 5G actually. So we're coming a little bit later and made possible what 5G had foreseen with a little bit too much good hope that this will come up in a very short time. So maybe, we are a little bit late. There is this gap, as we mentioned, between the research vision and what actually can be delivered in the market. So some of the bold vision that were already in 5G might become possible in a 6G timeframe.
Yeah, I heard somebody recently comment that while telecoms is working in 10-year cycles, in heavy industry, it works in 20-year replacement cycles. So it may well be, as you say, that that as we're improving the performance that we can deliver to industry, they're going to be getting more used to what we're delivering. So yeah, this whole gradual process through 5G and into 6G is going to be I guess the opportunity to really start engaging with other industries, because organizations like the 5G AA for automotive and 5G ACIA for heavy industry, they I think if you talk to them behind closed doors, they do say they kicked off a little bit late once the standards were already being baked. So so they kind of had to go to these other industries and go, this is what we've got, what can you do with it? Rather than asking them what they needed.
Yes, standard, they offer all those advanced features if you look at the specs, but the products that are actually available out there are not really coping with the latest features in the standard. And this has generated maybe some disappointment as well from the verticals that were expecting the capabilities a bit more advanced than what they were actually sold. So as you said, there is this gap, this delay that has brought to lower a little bit the expectation, and probably will be solved in the coming years, hopefully.
If we look at the deployment of the 5G base stations, number one, plus 90% of population coverage is China, and number two, followed by US. Asia is picking the next, and Southeast Asia, particularly in the third set. And Europe is far behind in terms of the deployment of 5G, particularly the mid-band. I'm not sure why. So I think Europe has to catch up lots. They are, I think, in the 30% coverage only based on this study from the Ericsson. I can share you that map. So it is quite triggering, right, in the case in terms of the deployment and also to experience the use cases. There's a lot of catch-up needed. China Telecom and Unicom, they have tested a lot of features. Network slicing, they already started quietly selling commercially the network slicing. So we hardly see anyone else or any mobile operators looking into the network slicing. To name the few mobile operators really up to the level is the Singtel, Deutsche Telekom, Verizon, AT&T, perhaps Vodafone, Orange. Right? So the rest of the mobile operators still needs to catch up a lot of things in the 5G, so that we can see and understand those experience from the commercial use cases, and that can be a good guideline for the research in the 6G as well. So anyone have any last word before we end, Jen? If not, I really thank all of you. Thank you so much. I really appreciate for your time. I'm so grateful to all of you to present today. I really appreciate for your time and effort as well. So with this, I would like to say thank you. And this video will be uploaded on the YouTube channel in a couple of hours. And I will post this in my LinkedIn and tag all of you. And I really hope that you can comment in our in the LinkedIn post, so that we'll have a greater reach out. So thank you so much. Have a nice day. And have a nice week. I really appreciate it. Have a nice day. Bye-bye.
Bye. Thanks, everyone. Bye.
Thank you. Bye.